Lesson 3.4, we're talking about zeros of polynomials. Back in lesson 3.3, we talked about synthetic division, dividing polynomials, and I promised you a trick that would help you to find those numbers that you would put on the outside of that synthetic division. And this lesson is me fulfilling that promise. So there is a theorem called the rational zero theorem. And so what it says is that if there is a rational zero to a polynomial, if there is a number that's going to go on the left side of that synthetic division that works, then it's always going to be in this form P over Q, where P over Q is just the constant term over the leading coefficient, right? And so it's really easy to look at this as an example. It's hard to sort of analyze that without an example. So let's look at the example here. Example 1, we want to list all the possible rational zeros. That means we're going to try and find all the possible numbers that, if we were doing synthetic division, what are the numbers that we're going to put out here? To find all of those possible rational zeros, what we're going to do is list all of the factors of the constant term. So we're going to make a fraction, okay? It's going to be positive or negative of any of these numbers. All of the factors of this term right here. So numbers that will divide 10. Every number that will divide 10 evenly are 1, 2, 5, and 10. And I'm talking about natural numbers, whole numbers that will divide 10. So 1, 2, 5, and 10. Over factors of the leading coefficient. So that's that negative 2 right there. What are all the factors of negative 2? Again, I have the plus or minus, so I'm already taking into account the positive, the negative, whatever. But numbers that will divide 2 are 1 and 2. And so now I'm just going to try and make every single combination that I can, plus or minus. So 1 over 1, that's a combination I could have, 1. I could have 1 over 2. That's one of the combinations. So 1, 2. I could have 2 over 1. That's already listed here, 2, right? I could have 2 over 2. That's already listed here. That's the 1. 2 over 2 is 1. I could have 5 over 1. 5. I could have 5 over 2. I could have 10 over 1. Or I could have 10 over 2. 10 over 2 is already listed. That's 5. I'm just trying to make every possible combination I can, right? Every single combination that I can make, I'm trying to make on this right side. So it's positive or negative of any of these. It looks like there's only 5, but there's actually 10 solutions listed here, 10 possible solutions. Positive 1, negative 1, positive 2, negative 2, positive 5, negative 5, positive 5 halves, negative 5 halves, positive 10, and negative 10. Those are all of the possible numbers, all the possible rational solutions. That means when I go to do synthetic division and I'm trying to find a number to put out here, I'm only going to pick from this list. I'm not going to pick any number that's not in that list. I would never try 3. I would never try 4. I would never try 7. If it's not in that list, I won't try it at all, right? If it's in that list, it could possibly work. For this problem specifically, you want to find 5 solutions, right? And so of those 5 solutions, some of them may be in this list. Some of them might not, because this is only giving us a list of the rational zeros. We could still have complex numbers or irrational, like the square root of 5 could be a 0, right? That's obviously not in that list. 3 plus I is not in that list, but it could be a solution. Those are all the possible rational, nice, easy solutions that we could get. List all the possible rational zeros. Take a second and see if you can figure this one out. It's the same concept as the last one. We want to do all the p's over q's. Factors of 8 over factors of negative 4. Here's what they are listed out. Positive or negative of any of those. And so even though I only have 1, 2, 3, 4, 5, 6 things listed, remember there are actually 12. It's positive of any of those or negative of any of those. I listed every combination in this top line, and then I just went through and simplified and got rid of the ones that were already listed. So for example, 8 over 4 is 2. That's already in the list, right? That was already in the list here. Those two are the same thing. We don't have to list them twice. The same thing here, 8 over 2, that's the same thing as 4. A lot of these will repeat. 2, that 4 over 2 is the same thing as 2 as well, right? Finding the zeros of a polynomial. All right, so here's what we'll do. We want to find the zeros. The way that we're going to find the zeros is by using synthetic division. And remember that if we get a remainder of 0, then we found a solution. We found a 0. The coefficients are 1, negative 4, 3, and 2. And I want to find a number that can go out here and work. I could try any number in the world, but the numbers that I'm going to try are p over q numbers, so that would be plus or minus 1 and 2 divide 2, and this coefficient is just 1, so just 1. So that'd be positive or negative 1, positive or negative 2. Those are the numbers that I'm going to try up here. I'm not going to try a 3, a 5, a 7, none of those numbers. We do still have to do a little bit of guessing and checking, okay? And so if we don't get it in the first try, that's fine. We'll just come back and try again. I'm just going to start with the easiest number, 1. Multiply, add, multiply, add, multiply, add. That did not give me 0, so positive 1 did not work. We can go back and try another number. Let's try a negative 1. Multiply, add, multiply, add, multiply, add. That also didn't work. So positive 1 didn't work, negative 1 didn't work. Let's try a positive 2. I'm just trying numbers out of this list. Multiply, add, multiply, add, multiply, add. Check. That did work. So positive 2 is a solution. It says find the zeros. We want 3 solutions here. So there's 2 that we don't see, right? We have 1 of them. We still need to find 2 more. I told you in the last lesson that once you get down to 3 terms, you're just as well doing star method, right? So if you could do star method, do it. And if not, we'll do quadratic formula. And so we're trying to multiply to negative 1 and add to negative 2. Negative 1 and 1 are the only numbers that'll multiply to negative 1. And so we just don't have numbers. We don't have numbers that'll work. Sometimes that's the case where star method doesn't work. And if it doesn't, we have to do quadratic formula. And here's what our quadratic formula looks like. X equals negative negative 2, which is positive 2, plus or minus square root. Negative 2 squared minus 4, 1, negative 1, all over 2a. That would be 4 plus 4 would be 8. And we could simplify that square root of 8. And so that's the same thing as 1 plus or minus square root 2. And now we do have 3 solutions. We have a 2, 1 plus square root of 2, and 1 minus square root of 2. If we wrote out the whole solution set, 2, 1 plus square root 2, 1 minus square root 2. We could type the 1 plus square root 2 and 1 minus square root 2 in our calculator and see about what that is. So 1 plus square root of 2 is about 2.4. 1 minus square root of 2 is about negative 0.4. And so those are our x-intercepts, right? Those are the solutions. Those are our x-intercepts. We have 3 of them. And so when we graph it, we can graph those 3 numbers. 2, 2.4, negative 0.4. So you see here we have 2, 2.4, negative 0.4. Those are our x-intercepts. So this doesn't give us like a surefire way to find all 3 solutions, right? It does tell us what the rational solutions are going to be. Notice that these are not rational. Any irrational solutions or complex solutions are always going to come in pairs like that. And so since I had 3 total solutions and I found 1, the other 2 are going to be accounted for by irrational solutions, or complex solutions. But we do know that our rational solutions at least are in that list, right? We can check all of those and try and find as many as we can before we go and do quadratic formula to find the complex or the irrational solutions. All right, same deal here. Find the zeros. I've already worked through and found 1 of them for you, right? The negative 1 does work. That's 1 of the x-intercepts. And we need 3, and so we need 2 more. To find the 2 more, you would have to do quadratic formula. This one is another one that you would try star method and it just wouldn't work. So you'd have to do quadratic formula to find the other 2. Those are going to be the irrational solutions. The numbers that you would check here, remember, are p over q numbers, p over q, where this is P and this is Q. And so it'd be plus or minus 1 and 2 over 1, which is the same thing as plus or minus 1 plus or minus 2. Same exact way that we started this one. 2 over 1, and here we have also 2 over 1. Find the zeros and their multiplicities. All right, so we should end up with 4. We should end up with 4 total solutions here. I wrote a negative 1 on here. I'm assuming that that works. So let's try. Remember that we're trying plus or minus. 1, 2, 3, 6 over 1, 2. It's these factors over those factors. And so my solution, my possible rational solutions are 1, 2, 3, 6, 1/2, 3/2. 2/2 is the same thing as 1, 6/2 same thing as 3. So any of those numbers are numbers that I could try. I would never try a 4 because it's not in the list. Never try a 5, a 7, a 9. Never try any of those numbers because they're not in that list of possible solutions, right? All that list is doing is narrowing down numbers to check on the left. Negative 1 is in the list, so we'll check it first. Bring down the 2. Multiply. Add. Multiply. Add. Multiply. Add. Multiply. Add. We need to find another number that works. Just because negative 1 worked once doesn't mean it can't work again. Why don't we try negative 1 again? Again, we're just trying things that are in this list. So bring down the 2. Multiply. Add. Multiply. Add. Wow, that hunch worked out great. Add. So negative 1 is actually a solution twice. That just means it has a multiplicity of 2. Negative 1 is accounts for 2 of my solutions, 2 of the 4 solutions. Now that I'm down to 3 terms, I'm always going to go and try a star method. I don't think it's going to work here, but I'm going to try it. Negative 12, 2, 2, 1. Oh my goodness, it's actually going to work. So I think positive 4 and negative 3 work. And so this is the same thing as 1 over 2. So that's the same as x plus 2, 2x minus 3. That gives us a negative 2 solution. That gives us a positive 3 over 2 solution. And then we had our negative 1 solution from up here. Notice that all of those were in our original list, right? We could have kept on going with synthetic division and found all those. I just prefer once I get down to 3 terms, I prefer to go on and do star method. That just speeds things up a bit instead of guessing and checking so much. It looks like we only have 3 solutions listed, and remember we needed 4, but the negative 1 accounts for 2 of them. It has a multiplicity of 2. Remember what that means for a graph as well. If it has an even multiplicity, it's going to bounce off that graph instead of passing through. So it's going to pass through here, pass through. It's going to pass through here because the multiplicity there is only 1. And it's going to bounce here. So if we look at the graph, it needs to pass through negative 2, bounce at negative 1, and then pass through 3/2. And that's exactly what it does. It passes through negative 2, bounces off at 1, passes through at 3/2. If we were to look at f of x as well to determine the end behavior, sort of putting together a lot of these pieces, this leading coefficient is positive, and so we know the right side is going to have to go up. This degree is even, and so we know the left side is going to have to go up. It's going to have to go up on the left and up on the right, and it absolutely does on that graph. Notice how we're pulling things here from 3.1 and 3.2 and 3.3. We're sort of adding all these things up to be able to graph these polynomials. This unit is very, it just builds on itself very well like that. It's all very cohesive. Try this one, see what you can do. Try and find all the solutions. Here, the numbers that you're trying, the numbers that you're attempting are positive or negative. 1, 2, 3, 4, 6, 12. Those all will divide 12 over 1, 2. So you're looking at things like 1, 2, 3, 4, 6, 12, 1/2, 3/2. Those are all of your possible rational solutions, right? Positive or negative of any of those. The first number I tried was 3. It looks like the 3 worked. And then I tried a -2, and the -2 worked as well. So then you get down to 3 terms. Those 3 terms turn into a quadratic. You really want to try star method, and it looks like star method does work as well. That's going to lead you to these 2 additional factors and these 2 additional solutions. So it looks like -2 actually would have worked again, right? So our total, all of our solutions are listed here. 3, -1/2, -2 has a multiplicity of 2. So of 4 solutions, all 4 solutions are listed here. All right, this says the old methods still work. Find all the zeros of the polynomial. This has 3 terms, so we could use star method from the beginning. We're already down to 3 terms. So I would have -3 on the top, -2 on the bottom, 1 and 1. We want to find 4 total solutions. -3 and +1 multiply to -3. They also add to 2. And so this gives me x squared minus 3, x squared plus 1. If I ever have one that I can just straight up factor from the beginning, I absolutely want to do that. It saves you so much time as opposed to doing synthetic division over and over until you find one that works. All right, so now what I can do to find all 4 solutions is I can say x squared minus 3 equals 0, x squared plus 1 equals 0, and so x squared equals 3, and so x equals plus or minus square root of 3 once I do the square root on both sides. X squared equals -1, x equals plus or minus I once I do the square root on both sides, and that's 4 solutions right there. That's all 4 of my solutions. Remember, when you do a square root on both sides, you do get a plus or minus. So I square root on both sides here to get to that next step. The numbers that you would be trying for P over Q if you were doing synthetic division would be 1 and 3 over 1. So that'd be plus or minus 1, plus or minus 3. And it just turns out that none of those work, right? Not a single one of those works. And so you have to use some other method. You have to go back and use star method and solve by taking the square root on both sides. All right, here's what this one looks like graphed. We do have plus or minus square root 3, and the square root of 3 in the calculator, that's about 1.7. So that's the same thing as 1.7, -1.7, and then these just can't be graphed, right? It should only have 2 x-intercepts. 2 real numbers were solutions, and so it should only have 2 x-intercepts. And it turns out it does. There's your positive square root of 3, your negative square root of 3, and your imaginary numbers, they're just not going to hit the x-intercept, right? It does cause the function to wobble a little bit there in the middle. If we looked at the end behavior, positive coefficient means going up. Even exponent means going up on the left as well, and that's exactly what it does. All right. The number of zeros of a polynomial, this is something that I've said over and over and over and over, right? But we just haven't put a theorem to it. If the degree of a polynomial is greater than 1, then you're going to have that many solutions, right? So if I have x to the 4th is my degree, 4 is my degree, I need 4 solutions, and there are my 4 solutions. That's the exact same problem that we had on that last slide, right? We knew we needed 4 solutions because the degree was 4. This is just putting a name to that theorem. Not all of them are real. Not all of them are like nice solutions, but we do have 4 solutions. We have 2 complex solutions and 2 irrational solutions. Those complex and irrational solutions, they do always come in pairs. That's what this is saying down here, is that if I had 3 plus I as a solution, then 3 minus I is a solution as well. It's always going to be the conjugate, right? The conjugate of that is going to be the solution. Anytime you have a complex solution, the conjugate of that solution is a solution as well. Anytime you have an irrational solution, the conjugate of that solution is going to be a solution as well. So if I had 2 plus square root 7, I knew that was a solution. Then 2 minus square root 7 is also a solution. All right, let's see the implications of this. Given that this is our function, right, and that 3 minus 4i is a solution, that means also 3 plus 4i is a solution, right? Find the remaining zeros. So there is a way that we could do this. We know that x minus 3 minus 4i, or plus 4i, are both factors, x minus 3 minus 4i. Both of those are factors because these two are solutions. that solution makes that factor, that solution makes that factor. If we multiply those together, we would end up with x squared minus 3 minus 4ix plus 3 minus 4ix, something like that, minus 9 minus 16i squared. So these two middle terms are going to cancel out. And we'd have x squared minus 9 plus 16, which would be x squared minus, let's see, 7. So x squared minus 7 is one of the factors. What we can do is use long division here and say x squared minus 7. We know it should divide x to the 4th minus 6x to the 3rd plus 28x squared minus 18x plus 75. Barring me doing something ridiculous in this math up here, which I very well could have, this should turn out to be a very nice answer. We should get a remainder of 0. I want to look at this math up top before I actually start to work and make sure that I didn't mess anything up. Minus 3, I think that's actually a plus 9 there. I'm glad I looked at it. That should be a plus 9. And that should be a plus 25. So x squared plus 25. All right, give me one more second. I'm going to do the same thing and just look at it for a second. Plus 9 minus 16i squared. Okay, I feel good about it now. So with long division, we want to divide, multiply, plus 25x squared, subtract, and bring down. I'm going to go ahead and bring down everything. Then divide again, multiply. Wow, that's going to be a big number, 6 times 25. That'd be minus 150x. Subtract. Bring down, that'd be 3x squared. Man, I don't feel great about this. Plus 132x plus 75. Oh man, that middle number is not going to go away, is it? If I multiply by 3, that would give me the 3x squared. That would give me the 75, but that number in the middle is not going to go away. Well, we can go back and try synthetic division and make sure that I didn't mess something up here. X minus 3 plus 4i. X minus 3 minus 4i. Plus 9 minus 16i squared. That'd be plus 25. Oh, good grief, what did I do? All right, well, let's try it with synthetic division and see what happens. With synthetic division, I would have still the same coefficients. 1, negative 6, 28, negative 18, 75. If you could find my mistake in this other math, please let me know, and I'll give you the bonus points for that. All right, so I first want to get x minus 3 plus 4i. So this 3 minus 4i should be a solution. Bring down the 1. Multiply 3 minus 4i. add, that would be negative 3 plus 4i. Multiply, that would be negative 9 oh good grief, plus 12i, so plus 24i, plus 16, that would be and then I want to add 28 to that. All right, I'm going back to the drawing board here. I'm glad you're getting to see me struggle. This is just how math is sometimes, you know. I'm going to go all the way back to here. I think I messed up on that step. I think that's where I made my mistake, because x squared plus 25 doesn't make sense. That would give me positive or negative square root of 25 as a solution, and not those imaginary numbers. So let's go all the way back here and try and redo that multiplication. I won't get in a rush this time. That's where I made my mistake. So multiplying, I get x squared minus 3x. I'm multiplying x by everything first. Then I'll multiply the negative 3 by everything, and then the 4i by everything. All right, so x squared minus 3x minus 4ix. That's multiplying x by everything. Now multiply the negative 3 by everything. Would be minus 3x plus 9 plus 12i. All right, now multiply 4i by everything. That would be plus 4ix minus 12i minus 16i squared. The good news is I see some things that cancel out here. The minus 4ix and plus 4ix. The plus 12i and minus 12i. All right, this is looking much better. This is the same thing as a plus 16, right? Minus 16i squared is the same thing as plus 16. X squared minus 6x plus 9. That makes the minus 6x plus 16. X squared minus 6x plus 25. All right, now we have our number. That's where I made my mistake. X squared minus 6x plus 25. X squared minus 6x plus 25 needs to go into x to the fourth minus 6x to the third plus 28x squared minus 18x plus 75. All right, divide, multiply, subtract, bring down, divide. Oh, this is looking so much better. Multiply, subtract, 0 remainder. Oh, yes. All right, now it says write it as a product of linear factors. Find the remaining zeros, part A. All right, so these are two factors. These are two solutions, right? Solution 1, solution 2. I need 4. My other two solutions are going to come from here. So x squared plus 3 equals 0. X squared equals negative 3. Again, I can square root on both sides. So then x equals plus or minus I square root 3. There's all 4 solutions. Write it as a product of linear factors. That would be the same as x plus 3. I'm sorry, I need to go back here. These are my first two factors. X minus 3 plus 4i. X minus 3 minus 4i. X minus I square root 3. X plus I square root 3. I just ran out of paper here, But these are my 4 factors, right? Those are the 4 factors that go with those solutions. Great. Whew. I'm glad we got that done. I had a feeling that it was somewhere around here that I'd made my mistake. I just got in too big of a rush there to multiply, and I lost that middle term, the minus 6x. That made all the difference when I went to divide. This was a difficult problem. I can say with confidence that you will not have one of this difficulty on your test, okay? So don't sweat that. I highly doubt even that there would be one on your homework that is this difficult, but this was a tough problem. It was a challenge. I'm glad we did it. All right, the next thing we need to look at is Descartes' rule of signs. What Descartes' rule of signs says, it's going to tell you how many of your solutions are going to be positive and how many of your solutions are going to be negative. This is talking strictly about real zeros, right? So not anything that's complex. So if we were given this polynomial, what we would do is we would start with synthetic division. We would say we need all the factors of 540 over all the factors of 1. And those are all listed right here. Those are all the possible rational solutions. Those are all of the possible rational solutions. Now, we can slim down our solution search even further by using Descartes' rule of signs. What it says is we're going to look at how many times the sign changes. So look, we go from a positive to a negative to a positive to a negative to a positive to a negative. That changed 1, 2, 3, 4, 5 signs. We flip from positive to negative to positive to negative. The sign of the coefficient changed 5 times overall. That means our number of positive solutions is going to be either 5 or reducing 5 by a positive even integer. So it could be either 5, 3, or 1. We can have 5, 3, or 1 positive solutions. That's our positive real solutions. We're going to have either 5, 3, or 1. We're not going to have 0, right? We're going to have at least 1 positive real solution. We may have 3 positive real solutions. We may have 5 positive real solutions. Our number of negative real solutions are, if we change the sign, this is a lot of like jargon here, but if we change the sign of all the odd powers, change sign. And then do that same rule again. So I would have negative x to the 5th. Not going to change the even powers. Negative 128 x to the 3rd. Not going to change the even power. Negative 783x. Not going to change the even powers. How many times does the sign change? A negative to a negative to a negative to a negative, negative, negative. The sign never changes, right? The sign never changes. That means I'm going to have 0, negative, real solutions. That means when I'm going through this list and trying to search, I'm not even going to try any of the negative ones, right? Since this sign negative never changed a single time, it was always negative, I'm going to have no negative solutions. Again, that's when you change the power of all the odd exponents. So I'm changing. This thing has an odd exponent. I'm going to change the sign of it. That one had an odd exponent. That one had an odd exponent. I'm changing those. And then I'm going to apply that same rule. Determine the number of possible positive and negative real solutions. So positive. We're not going to change anything. We're just going to look. It changed from positive to negative, negative to positive, positive to negative, negative to positive, positive to negative. Every single time it changed. That's 1, 2, 3, 4, 5 times it changed. It's going to have either 5 or 3 or 1. I'm always going down by 2 every time, right? It's going to have 5 or 3 or 1 positive real solutions. Negative real solutions. Negative. So I'm going to change all of these, all the odd exponents. Negative x to the 5th. Not going to change the even ones. Negative 12x to the 3rd. That's an odd exponent. X squared is an even exponent. Not going to change it. 11x, that's an odd exponent. Minus 6. How many times does it change now? It never changes, right? And so there are 0 negative real solutions. It doesn't tell us what the solutions are, but it tells us how many there are. And so when I go to do my solution search, I know I'm going to have P over Q. I'm going to have positive or negative 6, let's see, it would be 1, 2, 3, 6, right? All the factors of that over the factors of that over 1. So that'd be positive or negative 1, positive or negative 2, positive or negative 3, positive or negative 6. Since there are no negative solutions, I can just check 1, 2, 3, and 6. Those are the numbers that I'm going to check when I do synthetic division. Determine the number of positive and negative real zeros. All right, see what you can do here. How many are there? How many possible positive and negative zeros are there? Here, the sign only changes twice, so there are either 2 or 0. Remember, you're going down by 2 every time, so there are either 2 or 0 positive solutions. Negative solutions. We change all the odd exponents. That sign changes 3 times, so there's either 3 or 1 negative solutions, negative real solutions, right? I hope this has helped in your solution search, right? Because last unit or last lesson, it sort of seemed like it was a crapshoot. You were going to have to just take a guess and swing. At least this unit, we're able to narrow that down a lot and say these are the ones that we're going to try.